In this video, we're going to talk about Le Chatelier's Principle. And Le Chatelier's Principle tells us that if we have a system that's at equilibrium and something happens to knock the system out of equilibrium, the reaction will shift in whatever direction it needs to shift to regain equilibrium. So remember, our reactions, right, if they can exist at equilibrium, right, if they're reversible, they will, they want to be there. That's what we were doing with reaction quotients in our last video, right? Looking at our concentrations, we can determine, is the reaction going to be, is it going to proceed towards products or towards reactants with the end goal of achieving equilibrium in mind. Here, we're saying it's at equilibrium. Something happens that causes it to no longer be in equilibrium. It wants to get back to equilibrium. So, Le Chatelier's Principle. So it tells us that when a stress, and we'll talk about different things that stress can be, is applied to a system that is at equilibrium, the reaction will shift in the direction that relieves that stress. So again, we're at equilibrium, it gets knocked out of equilibrium. So a stress is applied, something happens that makes it no longer at equilibrium. The reaction will then shift in whatever direction it needs to get back to equilibrium in the direction that relieves that stress. We're going to look at three different things that stress can be. One is changes in concentration. Remember, at equilibrium, our ratio of products over reactants is always going to be the same. So if you change the concentration of one of the reactants or products, we no longer have that ratio, right? We're no longer equal to Kc, we're now equal to Qc instead. So it's going to shift in whatever direction it needs to get back. So changes in concentration. The addition of a reactant or removal of a product will cause the equilibrium, will cause the system to shift towards products. I like to think about it as undoing what we did, right? I want that certain ratio. I want my ratio of products over reactants to always be the same. So if we add a reactant, we now have too much. So we need to decrease the amount of reactant, increase the amount of product. So we're going to go towards products. If we remove a product, we now don't have enough product. So we need to make more, right? Or think about it as removing reactants, right? We want that ratio to be the same. Either way, we're going to have to shift towards products. So if we remove a product or add a reactant, in both of those cases, in order to undo what we just did, we're going to shift towards products. And the opposite, if we add a product, we have too much, so we're going to shift towards reactants. If we remove a reactant, we don't have enough, so we will shift towards reactants. So the addition of a product or removal of a reactant will cause the system to shift towards reactants. So again, we need to relieve that stress, essentially undo what we just did. So if I add a product, I have too much of them, so we're going to shift towards reactants, right, to decrease products. If I remove a reactant, I don't have enough of it, so we're going to shift towards reactants to make more of it. We need to relieve that stress. An example for us. I'm going to have N2, which is a gas, plus 3 hydrogen, which is also a gas, going to 2 ammonia, also a gas. So then our question is, which way will the equilibrium, oh, that's a tongue tire. Which way will the equilibrium shift if a nitrogen, that's an N2, is removed? The other way you can kind of think about it is you need to keep this level. This is kind of a weird way to see it, but if you're a visual learner, this might work. Kind of think of it almost as like a seesaw or a teeter-totter, where like this is the fulcrum and it needs to stay even. Now, be careful with this. Remember, at equilibrium, my concentrations don't have to be the same, but we'll say once we've reached that balance, I want to keep it balanced. So if you remove this, right, this side becomes too light and is going to tip down, which means to get it back to being even, I have to increase weight on this side, right, because I don't have enough. So I'm going to shift towards that side. So if I remove N2, right, I've removed, it didn't really look like 2, I removed a reactant, it's going to shift towards reactants. If I remove hydrogen, same shift. Let's say we add ammonia. If you want to think of that kind of keeping it balanced analogy, right? If I'm adding this side just got too heavy, so that side went down. I need to lighten up that side or make the other side heavier, however we want to do it. But we're going to have to shift in this direction. Again, you can also just thinking about it as having to undo what we did. If we have too much product, we need less product. So shift towards reactants. C, let's say we remove ammonia, right? Now I don't have enough on this side because I removed some, so I need to shift towards it. And then one other, we can add nitrogen or add hydrogen, same effect. It doesn't really matter. We're going to shift in the same direction for both of those, right? We're making this side too heavy, right? We have too much of this. We need to decrease it, so we need to shift away from it. Shifts towards products. So changes in concentration. The second stress that we're going to look at is changes in volume or pressure. Remember that volume and pressure are inversely related, right? If you have less volume, your particles that are moving around, right, are going to bang into each other more. They're going to bang into the sides of the container more, right, because I have less space to move around in, so my pressure is going to increase, right? You would have learned that during your gas law chapter in 150 or 151. This is only going to apply to moles of gas. So if you have species that are aqueous solutions, then this change is not going to affect them. So when volume is decreased, so our particles have less space to move around in, right? Pressure is increased. And again, this is only for gases. Equilibrium shifts towards the side with fewer number of moles. Fewer number of moles of gas. So if our volume is less, right, our pressure is increased, we're going to favor the side with the fewer number of moles, right? There's less room, we're going to favor the side with less stuff. And then the opposite is true, right? When volume is increased, we now have more room, so less pressure, right? Less collisions. Pressure is decreased. Equilibrium shifts towards the side. And by side, I mean reactants or products with the larger number of moles of gas. So our volume is increased, less collisions, so pressure is decreased. We're going to favor the side that has more stuff, right? The larger number of moles of gas. An example for us, N2O4, that's a G. And then 2 NO2 gases. So kind of the same thing, which way will it shift if, so our first one, we have, let's say the volume is decreased. Remember, this time we want the side that has less moles of gas. And if we look, right, there's a 1 here. So this side I have 1 mole of gas. On this side, I have 2, not 3, I can count, right? There's a 2 here, 2 moles of gas. If there was 2 like actual products, and they were both gases, I would add them together. If we go back up and look at this one, let's just look at this real quick. On this side, if we were to add a gas question to this one, I actually have 4 moles of gas, right? I have 1 nitrogen and I have 3 hydrogen. All of those are gases, right? They both have G's after them, so 4 moles of gas on that side. On this side, I have 2 moles of gas. If just for kicks, let's say nitrogen was a liquid instead of a gas, then I would only have 3 on the reactant side because I wouldn't include nitrogen, right? We're only going to include ones that have the G after it, only the ones that are in the form of a gas. Going back to this example, volume's decreased because I have fewer number of moles on the reactant side. It's going to shift towards reactants, right? The side that has the fewer moles of gas. If volume is increased, it's going to shift towards the side that has more moles of gas, towards products. And remember, the reason this matters is that we can express our equilibrium constant in terms of partial pressures. So if you're changing that pressure, right, if your pressure is decreased or your pressure is increased, which is what happens when we change our volume, then that ratio again is off, right? We can express it in terms of concentration or partial pressures. Ratio of your partial pressures for products over reactants, right, is always going to be the same at equilibrium. So if you change those pressures, you're going to knock it out of equilibrium and you're going to shift in whatever direction you need to regain that equilibrium. So less room, right, higher pressure, shift towards the side that has less moles of gas. That is going to decrease that pressure. If your volume is increased, right, I now have less pressure. To get that ratio back, we're going to shift towards the sides that have more moles of gas to increase that pressure, right? We want to undo what we did. Last stress, we're going to talk about our changes in temperature. And for changes in temperature, it is going to matter if it's an endothermic or an exothermic reaction. So endothermic ones first. Remember, if something is endothermic, it's gaining heat energy. Our endothermic reactions are going to have positive values for my enthalpy change, right? Because my enthalpy when I'm done is greater than my enthalpy when I started. So for endothermic reactions, we're gaining heat energy. I'm going to think of heat as a reactant, right? It's something we're putting into the reaction. So it gains heat energy. And I'm going to think of heat as a reactant. So if I wanted to write it, I would say heat plus reactants go to products, right? I'm gaining heat. Heat is something I'm putting into it. I'm going to leave some space because I'm going to come back and I'm going to write 2 lines there. So just leave yourself a little bit of space also. For exothermic reactions, right? These are ones that are going to have a negative value for my enthalpy change, right? These have lost heat energy. So my enthalpy when I'm done is less than my enthalpy when I started. So I have a negative change. So these lost or gave off heat energy. I'm going to think of heat as a Think of heat as a product, right? It's something I'm producing, it's something I'm giving off, right? So this one, I would have reactants going to products plus heat, right? Heat is something we're producing, right? Exothermic, it's gaining it, right? We're putting it into the reaction. Exothermic is something we're giving off. It's a product, right? It's something we're getting out of the reaction. So if you change the temperature, right, we're changing the amount of heat. If it's exothermic and you increase the temperature, I guess I said exothermic. If it's exothermic and you increase the temperature, right, I'm increasing essentially a product. I'm making this side, if you think about it as being balanced, too heavy, right? I have too much heat. I need to decrease that by shifting in this direction, right? If I decrease the temperature, I have less on this side, right? Heat's gone down. I need to shift in this direction. I will come back and write that down. For an endothermic reaction, those are going to be the opposite, right? If I increase temperature, this time the reactant side is too heavy, right? I have too much over here. I need to go in this direction. If I decrease my temperature, I don't have enough heat. This side is too light. I need to go towards it to make more heat. So you do need to consider whether it's endothermic or exothermic when you're given a change in temperature, because they're going to shift in opposite directions depending on if heat's something you're putting into it or something you're getting out of it. So let's write all of that down. So an increase in temperature, and this is under exothermic, let's indent it, or endothermic, sorry. Increase in temperature. The reaction shifts towards products. And then the opposite, if I have a decrease in temperature, now I don't have enough on my reactant side. It needs to shift towards reactants. And then for exothermic, it's going to be the opposite. I know I do go pretty fast, so please make sure that you're pausing the video if you need to be able to keep up. I do want to make sure that you get everything written down. So increasing temperature, right? This time heat is over here, so I have too much on the product side. I need to go towards reactants. And then decrease. The reaction shifts towards products, right? We're thinking of heat as a product. I don't have enough heat. We need to make more then, because we have to undo it. I'm going to go towards products. So let's look at an example. And I'm going to combine all three of these into one big example here for us. So our equation, I have 2 chlorine gas plus 2 water, also a gas, going to 4 hydrogen chloride, which is also a gas. Right, it has to be aqueous to be hydrochloric acid, plus oxygen, which is also a gas. And then we're told that our enthalpy change for this reaction is 113 kilojoules per mole. And then we want to say which way will it shift under the following conditions, and I have a bunch of them. So let me just list them here real quick and then we'll go through it. So the first one, temperature is increased. I'm just going to use a T for temperature. B, volume is increased. C, pressure is increased. D, hydrogen chloride is added. I have a lot of them, I think I said that. E, catalyst is added. Oh, we haven't talked about catalyst yet. We will. Sorry, I missed that. F, chlorine is added. And then G, water is removed. So what I would like you to do is try to answer this on your own, with the exception of the catalyst one. Let me put a little asterisk on this. So just skip E for now, but these others, please try to answer it. So hit pause, go through these. Is it good to go towards reactant or products? You can just put an R or a P for reactant or products. And then after you've gone through it, just hit play again, and we can look at the answers. So hopefully you guys get a chance to go through it. So temperature, again, remember with temperature, it's going to matter whether it's exothermic or endothermic. And if I look at my value for my enthalpy change, it's a positive value. Remember, if it's positive, that means that it's endothermic, right? In the end, I have more heat than we started, so heat is something I put into the reaction. And I'm gonna actually just move my example out of the way, because I actually want to write the word heat here. So because it's endothermic, right, I have a positive value for delta H. It's endothermic. So I'm going to think of heat as a reactant. So now when I go to do this, right, if I'm increasing my temperature, I'm increasing the reactant side. I need to undo that, and I'm going to shift towards products. So I'm just writing down the direction that it's going to shift. Sorry, I didn't write down the instructions for the problem, but the question is determine which direction the reaction will shift to get back to equilibrium under the following stresses, something like that. Volume, remember with volume, we're going to look at the number of moles of gas. And everything's a gas, so we're good. If for some reason, let's say water was a liquid, I'm going to change this, but let's just say water was a liquid, then I would ignore this, right? Because I'm only going to be looking at moles of gas. But since I have everything as a gas, I'm just going to count all of those. So I have 2 moles of gas plus another 2 moles of gas. So 4 moles of gas. On this side, I have 4 moles here. I have 1 mole here. So I actually have 5 moles of gas. So if I'm increasing my volume, right, volume's getting bigger, which means my pressure is getting less, I'm going to favor the side that has more moles. So I'm going to shift towards products, right, because it has 5 moles of gas versus 4. Pressure is increased, right? So I have too much pressure. I need to decrease pressure by shifting towards the side that has less moles of gas. So this one is going to go towards reactants. I'm adding hydrogen chloride. I almost said hydrochloric acid. So HCl is added. HCl is a product. So I have too much product, right? We added something to the product side. I need to shift away from that to decrease the amount of product that we've added. So it's going to go towards reactants. Catalyst will come back to. Chlorine, we're going to find where chlorine is. Chlorine is a reactant. Oop, wrong one. I'm adding it. So I have too much on my reactant side. We need to decrease that by shifting away from it. So it's going to go towards products. And then water is removed. Water is a reactant. I have less reactant now, right? I'm removing it. So my reactant side got lighter, right? I have less on the reactant side. I need to shift towards reactants to make more of it. Again, watch out for this. I'm going to change it, but I'll put it back, right? If water was a liquid, right? If water was not a gas or an aqueous solution, right? If it was a liquid or a solid, I would actually say no change, right? Remember, solids and liquids are not part of my equilibrium constant expression, right? We're looking for that ratio to be the same, but if it's a liquid or a solid, it's not part of that ratio. So it would be no shift, right? These things only affect species that are part of my equilibrium constant expression. So again, if water was a solid or a liquid here, my answer to part G would actually be no shift at all. So let's look at catalysts real quick. Hopefully you guys did okay on that problem. And then we will come back to that. So remember, catalysts speed up the rate of our reaction, right? There's something that we put into our reaction and then we get them back out of the reaction, and their purpose is to increase our rate. They increase the rate though in both directions, right? If I was to look at my energy profile, so I have energy and then my reactions proceeding, and then we'll just do a one-step reaction and we'll make it exothermic. So my reactants, my products, my transition state and my products. And then if I was to draw another line saying if I added a catalyst, what would happen? Remember, catalysts often act by decreasing that activation energy. So my transition state I have lower now, instead of my activation energy being the energy difference between here and here, it's now the energy difference between here and here, right? That is a smaller change than when I had it originally. So my catalyst is speeding up my reaction by lowering my activation energy. If I look at this reaction as being a reversible reaction, this is then my reactants, this is then my products, and my activation energy is still reduced, right? Instead of my activation energy being this difference, it's now this difference. So the catalyst is actually not affecting the equilibrium. It's speeding it up in the forward direction. It's also speeding it up in the reverse direction. So those two rates are still equal to each other. So a catalyst, right? It occurs, when I say it occurs, I'm talking about its role of speeding up the rate of my reaction by lowering its activation energy. To the same extent in both the forward and reverse directions. So as a result, it's going to reduce the time that it takes to go to reactants. It's also going to take the time that it goes to products, right? From reactants to products, products to reactants. It's reducing the time for both of those directions equally. Because of that, it actually has no effect on the position of my equilibrium. Right? We could draw those on there. I know I was just using my pointer before, but if this was the activation energy, right, the difference here in my reverse direction with the catalyst, right, that is now my activation energy. So it lowered it in the reverse direction. I know I'm doing reverse first, which is kind of weird. If I look at the forward direction, right, that was my activation energy. Adding the catalyst lowered it in that direction also. And then if we look, right, this is the same amount as that. So I've increased it equally in both directions. So the rate in both directions are still equal. We're still at equilibrium. I have no effect. So going back up to that problem, addition of a catalyst, there is no shift. So we should actually write that. Things that don't, right? Remember, solids and liquids are not part of the equilibrium expression, right? Not part of our law of mass action. So changes in the amount of solid and liquid reactants and products have no effect on the position of the equilibrium. So things that are where our answer is going to be no shift, right? If we have a solid or a liquid and we add reactants, we add product, as long as they're solids or reactants, solids or liquids, there's going to be no shift. Add them, remove them, it doesn't matter, no effect because they're not part of my expression. And then catalysts, because I'm increasing my rate, right, decreasing my activation energy by the same amount in both directions, it has no effect on the position of my equilibrium. So let's make a quick little summary. If I can write summary, that's a U. So this is going to be kind of shorthand notation, but concentration. So concentration changes or changes in concentration. If we add, and I'm just going to use R for reactant, or if we remove product, so P for product, it's going to shift towards products. If we add a product or remove a reactant, shifts towards reactants, right? We need to undo what we just did. If we look at volume, pressure, so if we have an increase in volume, so V for volume, which is a decrease in pressure, we're going to shift to the side with more moles of gas. Right? I have more room, I don't have enough pressure, we need to increase that pressure, so we're going to go towards the side that has more gas moles. And then opposite, if we decrease volume, increase pressure, sorry about all the abbreviating here, we're going to shift to the side with less gas moles. So a couple key things here, be really careful. Ignore pure solids and liquids, right? If you're given one of those, your answer is no shift. And you could be given one of those. I want you to know that there's no shift because it's not part of my expression. And this is for gas moles only. Temperature. So again, remember here, it matters if it's endothermic or exothermic. So if we increase temperature, so T for temperature, shifts towards products if endothermic. Shifts towards reactants if exothermic. If we decrease temperature, the opposite of what we just wrote, shifts towards reactants if endothermic shift towards products if exothermic. And then we'll add catalyst here. We'll just give you half a second. So if a catalyst is added, there is going to be no shift. Again, remember, if we have a solid or a liquid and I say we add or remove those, also no shift.